Hi, everyone. So I'm Siyao, PhD student from the Marx Institute at Western Sydney University. So today I'm going to briefly talk about the first experiment of my PhD project, which explored the discriminability, iconicity, and complexity of 10 different music notations and the underlying factors. So as we know that actually lots of music notations have been developed to address the some complexities associated with conventional staff notation. However, there has been little empirical research investigating and especially assessing and comparing the effectiveness of staff notation versus these alternative notation methods. So in my study, three main features were assessed for these different music notations, which are discriminability, iconicity, and complexity. So discriminability here describes how well participants can discriminate the changes in pitch and duration. So it is therefore measured by a visual discrimination task where participants have to decide whether the two notation excerpts presented on the screen for 750 milliseconds. They need to decide whether they are the same or different. And iconicity here describes how well a notation can be matched with the melody. So it is therefore measured by a notation melody matching task, where participants need to choose one of the notation excerpts that they think match with the melody. So they could just choose based on their own intuition. So complexity in the study was measured by the subjective complexity ratings on the 5-point Likert scale for different music notations. So this whole experiment was conducted online, and we collected 213 valid responses. The age range of participants was from 18 to 81 years old. We also used Gold MSI to measure participants' musical sophistication, and their GMSI scores was varied from 30 to 117 points. So we selected 8 existing music notations as well as created 2 novel notation systems. And we also prepared 20 pairs of notation sequences for each notation. Some of them differed in pitch, some of them differed in duration, and some of them differed in both pitch and duration. So here is the figure gives us an example of all those 10 different notations representing the same musical excerpt. So we collected participants' demographic information, GMSI scores, as well as the familiarity to different types of music notations first. And then participants went through 4 different blocks of 4 different music notations for each task. And after that, we gave participants the complexity ratings, and as well as an open question asking their favorite and least favorite notations and the reasons for that. So the Bayesian regression models indicated very strong evidence that piano roll notation, staff notation, and proportional notation had the best overall performance with relatively high discriminability and high iconicity, but low complexities. We also found a negative correlation between the task accuracy and complexity ratings, meaning that if participants, the better the participants perform in the experimental tasks, the less complexity they perceived. Since we also collected their familiarity to different music notations, we also analyzed this factor, but there was no main effect of familiarity, but a positive effect on the staff notation in both tasks, as well as positive effects on proportional and piano roll notation in the iconicity task. And since our participants cover a very broad range of age and musical sophistication, we also analyzed these 2 predictors. So the results of the effect of the musical sophistication suggested that it didn't affect the results of the discriminability, which kind of was reasonable because we only define discriminability in the visual aspect. But musical sophistication had a positive effect on the results of the iconicity task. So if you are like high musical sophisticated, you would perform better in the iconicity task. So as for age, age actually affects both tasks in that it had a positive effect in the iconicity task, but a negative effect in the discriminability task. So overall, our results suggested very interesting results of the different music notations in their different in their discriminability, iconicity, and complexity. But since we only analyze the pitch and duration dimensions, and also we only use relatively simple musical excerpts, so future research with more music features and more complex musical excerpts are needed to comprehensively understand the advantages and limitations of these different musical notations in order to guide us better in the use of these different types of music notations for different users and in different musical activities. So that's pretty much all I want to share today. So thanks to all my supervisors and thanks for this opportunity to present. Thank you.
So hi everyone, I'm Jen and I'm a PhD student at UQ, and today I'll just be presenting a brief overview of one of my PhD studies, which looked at semantic processing during vocal music listening in young and older adults. So vocal music or songs are one of the most common types of music that we encounter and engage with every day. And as we know, they're composed of a lyric component and a melodic component that are strongly bound together into a unified representation. So this has made songs an excellent opportunity for researchers to study the interactions between music and language. And previous studies have shown that the musical context can affect language processing. And this can happen at the phonemic, semantic, syntactic, and also the conceptual level. So I'll just give an example of one of these studies. So the study done by Paul and Sharna in 2005 presented short songs to participants and asked them to complete a lexical decision task on the final word of the song. So this is when participants decide whether the word is a real word or a made-up word. So the final word was either semantically related or unrelated to the context of the lyrics. And in addition to manipulating the semantic relatedness, they also manipulated the harmonic expectancy of the final chord so that, yeah, it was expected or unexpected. And they found that participants responded faster when the final word was semantically related than unrelated, which is consistent with semantic priming effects. But this effect was also further enhanced when the harmonic context was expected. So this is an example of how the musical context can affect language processing. However, one limitation of previous studies is that they've often used simple songs and experimenter composed songs that are unfamiliar to participants, and this doesn't really reflect the complexity of the music and songs that we listen to every day. And the majority of these studies have been conducted with healthy younger adults, and it has not yet been looked at in healthy older adults. So the aims of this study were to investigate the effects of music and spoken lyrics on semantic word processing, and whether semantic priming occurs when listening to pop songs, and also whether this changes with age. So in this study, we recruited two groups of participants, and they completed an online study using a semantic priming paradigm and a lexical decision task. So I'll go through an example of that. So what happened in the experiment was participants heard a short excerpt of a song, And this could be presented either in the original song format or as spoken lyrics. Then a word came up on the screen and they had to decide whether it's a real word or a made word. And the target word could be in one of 4 conditions. So the original lyrics to the excerpt, so in this case, it would be sack, a semantically related noun, for example, bag, or a semantically unrelated noun like tree, or a pseudo word. So our results showed that participants had overall high performance and accuracy in the lexical decision task, although our performance accuracy was slightly lower for pseudo words than the other 3 real word conditions, which is what we commonly see in lexical decision tasks. But there were no significant main effect of age. So in terms of accuracy, older and younger adults performed similarly. When we looked at reaction time, we found that young adults generally had faster responses than older adults, which is, again, commonly seen in behavioural studies. And both groups showed faster responses after listening to a song prime than a spoken lyrics prime, and this difference was larger for older adults. Interestingly, we didn't see any semantic priming effects in either age groups. So across all the 3 real word conditions, participants performed similarly. And this is interesting because given the robustness of semantic priming effects in previous literature, we did expect to see faster responses in the original and related word conditions. So some limitations of the study is using an online study may introduce variability in the equipment and potentially the attention that participants pay to the experiments. We've proposed that the lack of semantic priming effects may be due to a lack of sensitivity in the behavioural measures. So future studies could consider using EEG to investigate semantic priming effects. So in summary, it appears that lyrics processing is relatively preserved in healthy ageing adults. And familiar vocal music may be able to facilitate the speed of word processing over spoken lyrics. This may be due to increased attention or anticipation of appearance of the target word. Semantic priming effects require some further investigation, and some potential implications of this research is looking at how vocal music can be used as an intervention for language recovery in stroke patients. Right, that's all, thank you.
Good morning, everybody. In this presentation, I'll be discussing my systematic review on how we measure absolute pitch, titled Conceptual Coherence, but Methodological Mayhem, a systematic review of absolute pitch methodology. This forms part of my PhD, which I'm completing here at the University of Melbourne, under the supervision of Sarah Wilson, Miriam Mosing, and Margaret Osborne. Absolute or perfect pitch, AP, has been extensively researched, and there's growing evidence to suggest a genetic component to it. However, research in this area has been hampered by a lack of consensus regarding the absolute pitch phenotype, or what exactly it is we're measuring when we're investigating AP. There also remains no gold standard task to measure the presence or extent of absolute pitch. So in this review, I aimed to explore the methods of pitch naming tasks for the classification of individuals with AP, and also to examine the way in which variability in methods impacts the AP phenotype. And on the right here, you can see my search strategy. Looking at published papers over the last 30 years, I identified 146 empirical papers investigating AP, which I included in the systematic review. And on this table, you can see that I had a total of 148 studies from these 146 papers, including a total of 20,797 participants across studies, over 6,000 of whom were classified by the authors as having AP. Now, the vast majority of studies, over 99%, agreed that absolute pitch refers to the ability to identify and or produce notes without the use of a reference tone. There is then this near universal consensus on our understanding of AP on a conceptual level, but this doesn't translate to universality in how we measure AP or the levels of accuracy required to possess it. Now, while my review looked at a variety of characteristics of pitch naming methods, today I'd like to focus on the impact of methodological choices on the AP phenotype. I'll do that first by looking at the accuracy thresholds by which AP membership is determined. In the figure here, we can see 84 studies for which accuracy thresholds were published. Looking at the shaded bars in green on the right, these represent the levels of accuracy required for participants to qualify as having AP for each study, ordered from the most to least stringent. So for the top entry, a participant must have scored 100% on that study's pitch naming task to be in the AP group for that study. Further down, participants would have been in the AP group if they scored at or above 85%. Entries in light green refer to studies in which credit was assigned for errors within one semitone of the correct response, meaning that those thresholds are less conservative. And as you can see, there's an extremely wide range of performance considered to constitute absolute pitch, from ceiling performance all the way down to just 33%. And while performance thresholds give us an idea of the potential limits of the AP phenotype, it's also informative to look at the actual performance of participants. I extracted the mean performance of the AP group for each available study and calculated the 95% confidence interval around the mean. And these are shown, that's shown in the forest plot here. So this shows studies reporting mean performance, with each point representing the mean for a single study. Again, you can see some variability here with range of performance from near ceiling down to around about 60%. What then does this mean for our understanding of the AP phenotype? While there's this near universal agreement regarding the conceptual definition of AP, there's no consensus regarding how this definition is operationalized in pitch naming tasks. Without a well-described phenotype that's accepted across the field, behavioral findings might not be comparable or replicable. Phenotyping is therefore vital for genetic research in particular to ensure that any shared genetic variance is related to absolute pitch itself. And some recommendations emerge regarding how we might best measure absolute pitch. Firstly, task characteristics should be consistently reported to allow other researchers to understand the conditions under which the determination of AP has been made, to allow us to make meaningful comparisons across studies. If choosing to assign credit to semitone errors, for example, it's also important to report raw accuracy so that studies can be more meaningfully compared. Where possible, we should use data-driven techniques to determine AP group membership rather than using thresholds, as these are necessarily arbitrary. Additional focus on intermediate pitch naming performance, or quasi-absolute pitch, will help to clarify the AP phenotype as well, as this goes towards addressing whether AP is categorical or lies along a continuum. Thank you.
All right, well, thanks for coming. A common property of Western music is the presence of the tonal hierarchy, or musical key, and the metric hierarchy, broadly rhythmic pulse. Now, despite largely being treated separately in research, they're actually connected in real music. Now, I discovered that in typical Western music, or rather, I substantiated in typical Western music that the tonal and metric hierarchies are aligned, forming a joint tonal metric hierarchy, such that pitches with high tonal stability are disproportionately likely to occur on points of high metric stability. This is just a figure demonstrating part of that, and I can give you references later if you're interested. But I was interested not only in, does that actually occur in music, but what are the actual psychological implications of it? So in other words, can listeners actually notice if you mess with that relationship? So I took some normal sounding source melodies, composed melodies, and then I started doing some phase shifting, where basically I fix the rhythmic pattern in place and then shift the pitch pattern to start on another note, like the second note, third note, so on, which means the pitch content of the melody is identical, but I've changed the starting point. That operation, importantly, manipulates the alignment of tonality and meter because it changes which beats the tonally strong or weak notes occur on. So for example, here we have an aligned version of the source melody, which is created by starting on the third note of the source melody, which is why I've got the arrow there on the third note. And if I shift that over such that it's now aligned leftward, you can see that it is actually the same pitch pattern and exactly the same rhythmic pattern, but it is actually slightly different in terms of the melody. And this is what it sounds like. Hopefully the sound is working. Did that work? I'm hoping it did. I clicked the share. Hooray! No tech troubles at all today. Okay, so that's the aligned version, and the correlation coefficient you see there, 0.51, indicates that this aligned version actually has a stronger tonal-metric alignment than the original source melody, which wasn't always the case, but sometimes occurred. Now, if instead I start on the fifth note, that gives rise to this misaligned version, where now we have a misaligned tonal and metric hierarchies. Still the original same pitch pattern, just started at a different point, and same rhythmic pattern. That one sounded like this. So they all sound vaguely acceptable. They're not sort of horrible sounding melodies, which sometimes I've used in the past. Importantly, for that original study, I did not use the source melody itself because that would confound the presence of a tonal metric shift or phase shift with the amount of tonal metric alignment. And sure enough, I found that listeners did in fact rate the aligned versions as having higher goodness and having a higher metric clarity, as in how clear is the beat, than the misaligned melodies, which sounded really cool. So I thought, okay, well, let's see if that actually holds up in an objective sense. That's a subjective rating of metric clarity, but how about if we test objectively to see how well people can tap along with these melodies and measure various aspects such as how often are they tapping near the beats, how long does it take for them to start tapping, because the idea is that they start listening to the melody. Once they find the beat, then they start tapping along with it. So the latency indicates how long did it take them to find the beat when listening to that melody. And then other ones, tempo and variability and a whole bunch of other different measures that we could look at. Now, I did an online version of the study at Murdoch University where I had 81 participants. I also had, Peter Fordresher ran up at SUNY Buffalo, 79 participants in person, right? So not online. And that was using FTAP software instead of what I was using, which is PsychoPy. But nonetheless, I'll show you what I got from the Murdoch study. And that was that there was traditionally statistically significant result of aligned melodies having more accurate taps than misaligned melodies. The Bayes factor wasn't quite as convincing, but there was something looked like it was showing up there in terms of accuracy. And in terms of latency, there was a stronger result in that people did start tapping sooner for the aligned melodies than for the misaligned melodies, which all sounded very promising, particularly finding that online. I thought, well, that's great. Now let's do it in person. And in person, we get pretty much nothing. So we look at the mean asynchrony, which is essentially the error. How far away from the beat are they? No real difference between aligned and misaligned here, labeled as high and low. It didn't matter if we changed the tempo, because one of the other things we did in the design was play the same melodies at different tempos. Obviously not the same melody for a given participant, but we did change the tempo such that it wasn't always aligning with one particular tempo. And that didn't change anything in the accuracy either. And same for the latency, pretty much. No real difference between aligned and misaligned, and it didn't really matter how fast it was being played either. So I was left with a rather confusing set of findings here, whereby we have tonal metric alignment affecting latency and accuracy somewhat for the online participants, but not for the in-person participants. Which was all rather very confusing for me because I expected, if anything, it would be the other way around. Given that the variability introduced by online studies where I have no control over the polling rate of their keyboard or the headphones they're listening to or using, or even if they're using headphones at all, you'd think that if you don't have control over those factors, that would mean you'd have a weaker result. So I'm not entirely sure what this really means for implications and where to go next steps. And that's kind of why I wanted to bring it to this conference, because I was hoping that maybe some of you might have some ideas on what on earth that might mean, how I might deal with it, and Yeah, and any ideas. So thanks for listening. Happy to expand on any further details of it if you'd like. Also have a bunch of references here, which I'm sure you can't see, but I'll leave it there for now. And yeah, I'll stop sharing, and I'm very interested in whatever questions you or input or questions you might have.